Hi, this is Jason with Liquid Instruments. This is the second video in a three-part series discussing how to create, train, and deploy an artificial neural network for signal analysis, using the neural network instrument available on Moku Pro. If you need assistance installing and setting up the Python API, then please see part 1 of this series. If it's installed and working properly, then you can start from this video. We're going to go step by step through a simple example of a neural network using the API commands to set up and train the model. As you can see, where we left off was at this first code block, where we've made a call to moku.nn to import two necessary commands, linModel and saveLin. So we're going to run that block. Now the first thing we need to do is generate 3 periodic signals and their sum to act as our training data. We've generated these 3 signals, which we call in1, in2, and in3, and these 3 separate signals will be our input to the model, and their sum, which is given by a summation of different weights of these 3 input signals, will be the expected answer. So we generate all that data by running this code block. And you can see the plots of the inputs and the desired output. So now we're going to develop a neural network that converts 3 inputs into 1 output. So we need to properly shape our data. We want the input data to be in the form n by 3, or an n by 3 matrix, and the output to be in the form of an n by 1 matrix, where n is the number of points that we determined in the first code block, which is 1024 in this case. This code block does exactly this operation for us, turning all 3 of these variables from vectors into NumPy arrays. So we run this. Now we actually have to build the model. The first step is calling the linModel class that we imported at the beginning of the script. We then use the command setTrainingData to specify the inputs and the expected answer, which we just generated in the previous code block. We don't need any I/O scaling in this example, so we're going to set this keyword argument to false. The next step is the model definition itself. In this case, we create a list which is titled Model Definition. Each element in the list is a tuple. That corresponds to a layer of the model. The first is a scalar, which defines the number of activations in that layer, and a string, which defines the activation function in that layer. You can have up to 5 layers of up to 100 neurons in each layer, and there are 5 activation functions to choose from: tanh, ReLU, linear, soft sine, and sigmoid. Now, since this is a very simple example, a single activation will actually give a perfect prediction. But if you want to try out different models and see what effect those have on the final answer, we have a few that are commented out with different numbers of neurons and activation functions, so you can test that out for yourself. We then use the command constructModel to build it, and a summary is going to be output below. You can see that information appear in the output. Now we need to train the model using the command fitModel. The number of epochs determines how many times the training data will be fed into the model. The variable validation split determines what percentage of the data will be held aside for validation. And this keyword argument esconfig contains other information that the model might be interested in. So the one that we've given here as an example is the patience, which can help terminate the testing if the model converges very quickly. Now we're going to run this training, and we see the epochs filling up very quickly, and we expect that this model converges very quickly. It may take a few seconds, so I'm going to make a cut to the model finishing. After this command finishes, we can plot the loss and the validation loss as a function of the number of epochs in this next code block. Now, since this is a very simple model, you can see it converges very quickly, and the error becomes quite small, on the order of 10 to the minus 15. For a quick visual validation, you can also use the command predict to generate an answer to a new data set. You can see that the error, if we run this command block, you can see the desired answer and the model output to be almost identical, and the error is on the order of a few parts in 1 in 100 million. So very accurate model in this case for this very simple example that we've generated. So the last thing we want to do is we want to use the command savelin. Again, one of those functions that we imported at the beginning of the script. And this will export the layers, the weights, the biases, and the activation functions into our own lin format, which is basically just a JSON file with some additional information. We tell the command which model to write, and we also specify the size of the input and output layers. So these will be matched to the physical inputs and channels of the instrument when we later load this onto the Moku device. Once the script exports the lin file, we can proceed with the next step of the sequence, where we load it onto a Moku Pro and test it with real data. For more information, check out liquidinstruments.com and stay tuned for part 3, where we will perform this task on a real Moku device. Thanks for watching.